Okay. So yeah, it's been a little bit because general meetings have been taking over our lessons. But we only have 2 more electrical component lessons before we start getting into the alt team and GitHub source tree related tutorials. So we're almost on to actually doing things. So for today, we'll be looking at, oh, I hate this. Looking at OpAmps, going through the few different configurations, being the well, I hate this. The non-inverting, inverting, we'll look at a simpler version, which is just a buffer, as well as the comparator. I'm gonna lose my shit while trying to write this, but we will also at the end look at the differential amplifier. Not in as much detail, but it slightly builds on the concepts of the inverting and non-inverting, so we'll take a look at that at the end. So to start off, your OpAmp symbol, you have a inverting and non-inverting pin. You have your supply rails, and you have your output. Normally, when we're drawing or normally on a schematic, you may not see your supply pins. In plenty of the non-inverting and comparator applications, these will get tied to whatever your VCC 5V usually is and ground. But in some applications that you'll use OpAmps in, having your V negative tied to ground isn't ideal, or isn't even feasible in some degree. Yeah. But simple 5-pin device, 2 inputs and output, and then your power ground. We have a few just basic rules to go along with an op-amp. They're basically fundamental properties of the op-amp that it always tries to that it'll always go by, even if regardless of what configuration you're set up in, just the general characteristics of an op-amp being that no current flows through your inputs. So that is, we have no current flow in or out of either of our input pins. Second rule being that it tries to keep the input voltages the same. That is, when you have a system of feedback, like we'll see in both the non-inverting and inverting, if we are applying some voltage to the first pin, and we have feedback on our second pin, we'll see that our output will change in such a way that our inverting pin will have the same voltage as our non-inverting pin. And then the kind of final thing that ties in to this second rule is the final, in an open loop, the gain is massive. For simplicity's sake, or in, practical, it's basically infinity. So that is, when we don't have a system of feedback, we don't have this tying back to us. Since we're not able to influence what's happening on our inverting pin if we're applying something to our non-inverting pin, it has basically an infinitely large gain, and will tie itself either high or low, which is the functional premise of a comparator. Any questions on the setup of an op-amp or the rules with it?
What's gain?
Gain, I'll mention it when we get to some of these the non-inverting and inverting systems. But gain basically is some multiplier from input to output. So that is, if we are, maybe should have done this the other way. We have some V in. We have our feedback loop, and we have our V out. The gain, which is denoted as AV, is going to be some multiplier of V into V out. So our V out is V in times some amount of gain. And I'll explain what the gain is in the different applications. Any other questions on anything, any of the rules? Do they make sense? Does the idea of rule number 1 make sense to everybody?
No, how does how can you have current? How can you have voltage but no current though? There's like number of electron flow. There's like no electron flow, but there's a voltage there. That doesn't quite make sense to me.
Yeah, exactly. This rule isn't one that really makes sense when you, or it shouldn't make sense when you first see it, because in this system, we are applying some amount of power to our input voltage. It's got nowhere to go. It's got nothing except going directly into that pin. But for somehow, we don't see any, we have no current flowing into that pin. And similarly, we don't have any flowing in or out of the inverting pin, although it should be tied to our output. We would assume there should be. What's happening is that the internal of the OpAmp has the inputs of both have high impedance. So basically they have a stupid high resistance values, while our supply pins are able to have a low impedance on the pin. So that is, the output is very good at sourcing and sinking the current. And the inputs have a high enough, they have such a high impedance that they basically don't impact the signal that's coming in. The op-amp as a whole, based on this premise of having high impedance inputs, low impedance output, makes it so it doesn't impact the system as a whole. Because you can imagine in our quick diagram, these resistance values have to be very specific to get the certain amount of gain that we're looking for. And if our op-amp were to eat up some current or add in resistance in any ways, that's going to mess with our values, and it's going to produce an undesired gain effect. So op-amps are designed in such a way that they have a large impedance so that they don't influence the rest of the circuit, but then can easily be able to send out the appropriate voltage and currents that are required.
How would it affect the rest of the circuit if it was like high impedance? Like, what does low impedance affect things?
So if we were, so if we were to say that our input has a low impedance, so it has some low resistance value internally, and then we were also using very low resistance values, like a 50 ohm and then a 100 ohm. These are low resistance values. So if this also has low impedance, even if it's also 100 ohm or sub 100 ohm even, the current path is, instead of going through and creating this voltage divider or whatever the system is going to be, the current, because it wants to follow the path of least resistance, it would rather go and sink itself into the op-amp. So by doing that, you would negate your voltage divider, or your resistance of the voltage divider changes, so the voltage that it produces isn't going to be what you're actually designing it to do. So then your output voltage is going to be something it's going to be some value that you're not actually going for. I'm sure there's other negative effects aside from just messing up the gain directly through this slight impedance difference. But that's kind of the big one to make a point of. Anything else? We'll kind of see how this matters when we get into showing the systems. But no other questions on the rules or how that's set up so far? Okay. And we'll jump into the easiest one, being the comparator. Now, there are dedicated ICs to being a comparator. They use op-amp logic to function, but your standard op-amp doesn't always like to be ran as a comparator, just because of how the operation is. So we have our op-amp, and in our system, and this will have our V1, V2, and then our Vout. And then in this case, again, we'll just say we're tied to 5 volts and ground. Now, if we are sending say 3 volts and 2 volts, because of our infinitely high gain, we see a difference of 1 volt between the two. And now that gain is getting amplified by infinity. So the output is going to want to see, or yeah, it's going to want to be, you know, some stupid high voltage. Obviously, we can't produce that stupid high voltage because we are capped by our supply voltage. So our output voltage is going to be 5 volts. It's just going to be an instant step up, hit 5 volts. Now, using a standard comparator, the cap on your output is typically less than, so you're not going to be able to achieve perfect 5 volt, 0 volt. It'll be 4.8 and 0.2. Like, it'll be slightly off, unless you get a rail-to-rail op-amp. A rail-to-rail op-amp is one that's specifically designed to allow hitting your supply. And we can see.
Hello?
And
Hello?
if we were 2 volts to the non-inverting and 3 volts. Yeah.
You were cutting out for a good bit. Like right after you mentioned rail to rail, you were gone.
Oh, was I?
Yeah.
Motherfucker. Okay, am I back though? Can you hear me?
You're back now.
Yeah.
Okay. I mean, I didn't mention much after the rail-to-rail. But yeah, so like the rail-to-rail is an op-amp that's designed specifically to be able to handle hitting your upper and lower supply voltages. So we can actually see this 5 volt output. And then if we go on to the next example where we apply 2 volts to the non-inverting and 3 volts to the inverting, what it's going to want to happen is see the difference of minus 1 volt, and again amplify that by infinity. So it's going to want to see a minus infinity voltage, but obviously is unable to do that. So now, if we were just sitting at our 5 volt, it's going to slam down, and we're now going to see 0 volts on our output. So it works in both. It works either direction you go. If we have a greater voltage on our non-inverting or our positive pin, the output is just going to be tied to the high rail, 5 volts. Whereas if our non-inverting is higher, so our negative pin, that's just going to pull us down to our negative supply. So in our case, ground. Now we use this in a couple places in our car, actually. Both on the BSPD and the T-cell, where we want to trigger at a certain threshold. So if we have we want something to happen after we hit 60 volts for the T-cell. We want an LED to turn on after 60 volts happens. And since we have our full range of being, 168 all the way down to 0 volts, but we only want it to happen once we get up to 60 and then stay on for the rest of the way. What we can do is basically take our negative pin and tie that to 60 volts, and take our positive pin and then just tie that to the battery. Obviously, we're not doing this directly because we don't have OpAmps that are handling 200 volts. But in the simplest form, if we tie, and then we have our LED. So while our battery is not connected, we'll see 0 volts. So we see our negative pin is greater, so it wants to just slam down to the negative supply. So we're going to just output 0 volts. LED stays off. Now, once our battery climbs to greater than 60, all of a sudden we now see that our positive is greater than our negative. We see that infinite gain, and it wants to slam high to its positive voltage rail, and it will send whatever that V plus, call it 5 volts still. And all of a sudden our LED turns on. Now, to avoid finding an op-amp that will allow 200 volts, the much easier solution we do is we supply 5 volts to our inverting pin, and we just create a voltage divider that's connected to battery. And we choose our resistor values in such a way that 60.1 volts here equates to 5.14 volts here, or whatever tolerance we decided to go with, to make sure that as soon as we pass that 60 volt threshold, our LED would turn on. Questions on the comparator? Makes sense on the use and how we take advantage of that open loop infinity gain.
Seems like you. Oh, go ahead.
Sorry, can you go over again? Like, what does it mean exactly? Like, what do you mean by open infinity gain?
Yeah, so because our system, it just has 2 inputs and our output that aren't, we don't have anything, we don't have a signal that ties our output to our input. Since we lack this, that means we have an open loop system. Basically, one continuous path, just going from input to output. No feedback, so it's open loop. And by definition, by one of the rules of an op-amp, its open loop gain is massive. So you'll actually find it in. You'll be able to find a number in a datasheet saying something about it, but like your open loop gain is typically good. Like it's going to tell you it's some 100 dB, I think they refer to it. So it basically wants to take whatever your input and multiply it by this massive number, because again, our output is just our input times some gain.
Okay, cool, thanks.
Yeah, so even if we were to be at 60.01, so we're only 10 milliamps above, 10 milliamps multiplied by 10,000 is still going to be a massive number beyond our supply voltage. So it doesn't take much of a difference to basically trigger this behavior. Andre, you had something?
So it's typically so when you apply an op amp, you don't use an op amp IC, right? You use a comparator IC because it's like a kind of a dedicated op amp for.
Yeah. There are actual comparator ICs which like they're still basically an op amp, but it's specially for running this rail to rail operation. But you are able to just take a normal op amp and force it to be a comparator. Good. Anything else on the comparator setup? Okay. That is the easiest kind of application, but not truly proper, or not really the way to view op amps, since their operation is better used in the feedback loop. That's where kind of the main use of them come from. So if we now look at a non-inverting, so what we have is we're sending our input to the non-inverting pin, and we have our output gets tied to our inverting pin through a series of resistors. We can make this even easier if we were to get rid of the resistors, and like I kind of went through, we have just a direct feedback line from output to input. When you do this, this is more known as a buffer. and we'll see why that is. Let me start going. So we have, we'll start with the buffer setup. We are applying some voltage, 3 volts, to our non-inverting pin. And by the rules, it wants to keep both its pins at the same voltage. So if we're applying 3 volts, our output, since it's tied directly to our non-inverting pin, it's going to want to drive it to also become 3 volts so that these two are balanced and they're happy. Doing that, if we have 3 volts on our non-inverting pin, our output will also be 3 volts. So what we get in this situation is a buffer has a gain of 1. Obviously nothing's going on. We just have 3 volts in, 3 volts out. Nothing happens. Our voltage stays as it was. The benefit to using this buffer circuit is if we have some small electronics on our input side. So if this is being driven by some small sensors that maybe like max they can only supply 5 milliamps. They're not able to source a whole lot, but we want to be able to drive, several LEDs on our output. Well, because of the output being powered by the supply rail of the OpAmp, we are able to source the power from the OpAmp, which you'll go through the data sheets, you'll find its voltage and current ratings, and maybe this OpAmp is able to source 100 milliamps. So we're able to drive the system on a 5 volt, 5 milliamp sensor, which is enough to trigger the OpAmp to send the exact same output voltage that we wanted to send originally, but now we're able to do so at a higher current so that it's more usable on our output side. So it doesn't impact the signal in any way. It purely just allows it to carry on at a higher current rating. Make sense?
Do you ever need to use buffers for impedance matching of more sensitive signals?
For impedance matching? Potentially. I don't think I can say for certain that would be the way to. Actually, yeah, potentially. If you have several different signals and you put a buffer to each one, they would all be able to then, all signals coming past the buffer would be sourced from the buffer, and they would all have a similar impedance moving forward. Surely there, yeah. I'm sure in a pinch that would probably technically work. Any other questions on the buffer?
What are your typical applications for the buffer?
Primarily exactly what we went through here. It's if you have something that is of low current and you don't want to distort it, you want to make sure you keep that same voltage range because maybe that's super important to get the actual sensor readings. But you just need to have a little bit more current so that it's actually able to drive something. You would use a buffer.
When do you use a MOSFET instead?
You could do that. But I think it comes down to how sensitive the signal is. If you're running some super small 5 milliamp 2 volt kind of sensor, like it's something quite small, where it may not even have enough to trigger the MOSFET, the buffer would be the ideal way to go. Probably not even size related, because at such low currents, MOSFETs can be just as small as some OpAmps. Yeah, I think
I know buffers usually come in multiples per package, whereas MOSFETs don't.
Yeah, I'm sure the packaging, the size and packaging has to do with it. You can get much finer op-amp packages compared to MOSFET. And then, probably sensitivity of the signals. If it's a much finer signal, you would run it through an op-amp. Not too sure on the power loss through the op-amp compared to the MOSFET. I know you can get MOSFETs with very low RDS ons, so potentially the power loss wouldn't be an issue compared to, but I can't say for certain. Well, then if we go back to we initially had, so now the true non-inverting. So again, we have our V in doing something or V out doing something. And we just have now this, that's an Ri square. We have this resistor setup, which is essentially just a voltage divider from our output going into our inverting pin. What we see now is that our gain is going to be R2 by R1 plus 1. You'll learn how that's properly derived in one of your classes. MC 251, I think, is where that is, or equivalent. You'll see why it's properly derived that way. But in short, we take it as our gain now is going to be R2 by R1 plus 1. And the plus 1 kind of makes sense when we look back to our buffer, because when we have a straight feedback line, no resistance, no nothing, R2 in that case is technically 0 by R1, which is infinity. So we have 0 by infinity, we have 0 in place of our resistors plus 1. And then we go up to the gain of a buffer and it's just 1. So it makes sense when you look at why the buffer just produces a gain of 1. Now what happens when we put values to this? Say we have a 9K and a 1K. Well, now we get a gain of 10. So if our input voltage now, of course, that means that our supply on our op amp has to be greater than 20 volts to actually be able to supply that. But we can see now that we just took a 2-volt signal and all of a sudden we're outputting 20 volts. Make sense to everybody? You know? Now, this does also work with AC voltages. So if instead of just sending a solid 20 volts, if we were sending an AC of 2 volts peak to peak, our output would match up just the same. Another 20 volts peak to peak. And it would be, if we were to throw this on, it would be perfectly overlaid no phase shift between our inputs and outputs. Now this is where, when you start to deal with AC voltages, is when your supply volts start to matter. Because if we, again, were just to have our supply volt, in this case, tied to ground, if we were to have this just tied to ground and we try to make this 20 volt peak to peak signal, which means you know 10 volt minus 10 volt. Well, if we tied our supply voltage down to 0 volts, tied it to ground, what we would actually see is input, and then it gets chopped at 0. We're no longer able to supply this required -10 volts to properly see our sine wave. So that's when it becomes important that if you're designing something that's specifically if you're designing something that has the AC, if that's using AC voltages, you have to make sure that the supply rails of the system are actually able to take what your expected outputs are meant to be. Make sense? We can shift to inverting op amp. So very similar, except now we have our and our inverting input gets the signal. Now with this is where we can start to see the rule of no current passing through our pins. So even if we are to supply 2 volts to this pin and we have, our 1 key on here, there is 2 milliamps here. There theoretically should be. But if we were to probe this pin, we would get nothing. We get 0 volts because we have forced our non-inverting to ground. That is hard set 0 volts. We can't influence this one. We only have the ability to impact the inverting input. This pin is going to be what's seen as a virtual ground. So it too is going to want to be 0 volts, no current allowed to flow. So that means all 2 milliamps proper current flow goes through the upper resistor. Again, R1, R2. So the inverting op amp is where we can kind of see it's important for the op amp to have a high impedance and to not allow current flow into its pins. Because you can imagine if we're pulling 2 milliamps at that node and impedance on the op amp is lower or even similar, the current flow is going to want to split between our resistor 2 and our op amp, and now the gain is going to be affected. And it's not going to be something predictable enough that we can just make it a constant and say it's not a problem. So the fact that it is high impedance and no current allowed to flow really benefits in the inverting op-amp configuration. We go through the current flow, and then we say we have a 10K on top. So 10K. We're going to see the voltage drop across our resistor. And at this node, we'll have our 20 milliamp, our 2 milliamp by 10K. We get a nice negative 20 volt. And we can see that the gain for the inverting is just R2 over R1. There's no extra +1, there's nothing to it. Just whatever we have for R2 divided by R1, invert it. So like we see here, our output is just going to be our 2 volts by our negative 10 over 1, so 10. So what we get is the minus 20 volt. And again, this is, the inverting is more important that we really consider our negative supply compared to the non-inverting, since the non-inverting took a positive signal and it just made it more positive. So we never had to worry about the negative unless we were dealing with AC signals. Whereas the inverting op-amp, you send it a positive and it's going to shoot out at a negative. So we have to be able to accept whatever negative voltage we're expecting. Make sense? Questions on the inverting op-amp? Can someone hazard a guess to maybe I can't supply minus 20 volts here, but I want to generate a 20 volt peak to peak sine signal like we did before. I want to be able to make this curve, but I don't want these chop offs. How am I able to do that if I, for some reason, don't have any access to a negative voltage? All I have is I can send this to ground. Any ideas? Start calling on people.
Maybe you can add another op-amp somewhere.
Potentially. That would complicate more than what we need to. Elena, any ideas?
No.
Koi?
None nothing so far. No idea.
Right.
Can you repeat the question?
I don't have access to minus 20 volts. All I can do is send my negative supply straight to ground, but I still want to be able to properly generate a 20 volt peak to peak sine wave. I don't want this chopping. What can I do to this?
What do you have access to on the positive side?
Say greater than 20 volts.
So wait, only 20 volts. You can change the ground reference.
We're saying that I can't do that. We're saying I can only send that to ground. I don't have negative
No,
voltages.
not like negative V, like the other side, the positive end of the op amp, or the positive input. Instead of tying that to 0, tie that to something else that would be seeing um the rest of the waveform, like half of the input, or like so it'll shift everything else up.
Yes.
It makes
Yeah,
sense in my head, but you should draw the you should also draw the graph.
Yeah, so Raphael also got that. Translate the wave up. So yeah, what we're wanting to do in this case is have it so our 0 point, and that our sine wave is now, instead of about being about 0 volts, it's now about 10 volts. So that we're now able to send it plus minus 20 volts. So we get our 20 volt peak to peak signal that we want. Now to accomplish that, like Andre was saying, you change our non-inverting pin. And the easiest way to do that is if we were to give that 20 volts, and then just say these are equal 10K, 10K, or E0 alternative, we just say we give this 10 volts. Now what we're doing is we're changing the reference point. Instead of being ground like it was, which centered it around ground, we're now offsetting by 10 volts. We are now basically adding 10 volts to our input signal. So whatever V1 was now gets shifted up by this 10 volts. So now we can see when we do that, we can see our full sine wave in all that we want it to be. There, you may have to do something further down the line if you want to center it back around 0 volts. But for the sake of all we have is, 30 volts in ground. This would be the way to make sure you get a full sine wave. Make sense? To all those that weren't sure of it, this idea of just changing our reference point to being something higher, so our entire signal is basically translated into our usable region. Makes sense? Okay. Then we can do our final op amp, which useful. I haven't done as much on the differential. It's slightly different compared to all of these other op amps, but the principles are the same, and it's just building on top of everything we've done. So it actually will look very similar to what we just drew up. That it basically takes both the setups we had and lays it onto one. So we'll have our 1 or 2, or 3 or 4, and then our output. So the idea to this is we have different voltage values coming in, constantly changing, maybe it is, and they're being basically compared to each other. So that is, maybe we're seeing 2 volts and we're seeing 2.5 volts. Maybe it is. Or whatever the system be, these are constantly changing voltages on our input, and we're going to compare and kind of take the difference. So the easiest scenario to this is all of our resistors are equal. So that being, maybe we just threw a 10K on all of these. This is known as the unity gain. And what that means is our output is just going to be the difference. There's unity gain just means gain of 1. So we get nothing special in this scenario. 2 minus 1.5. Our output is just going to see half a volt. So it's able to take in our 2 signals, basically pull the difference between them, and output that as just a solid. So now we're able to read half a volt on our output. Now, the more useful cases, if we assume, well, actually just starting off, just in general, what we have is V2, a long mess of shit, R2, R4, by R4, by R1, R3, R1, minus V1, R3, R1. So you can imagine if we were to give all of these different resistor values, you would have a little bit of a mess of an equation to figure out what our actual gain is. The more typical setup is when we have R1, R2 equal, and then R3, R4 equal. So what that looks like is now going to be our output is just going to be R3, R1 by V2, V1, multiplied by V2 minus V1. So now we can see that our gain, did I write these all proper? Yeah. Our gain is now the same thing as what it was, so it's just our difference between the two voltages, now multiplied by some R3 by 1, R1 ratio to give it a gain. Now this is where it's more used, because in the case of maybe they're just very fine signals, so instead of 1.5 and 2, we are running with 2.02 and 2 volts. So now we just have a difference of milliohms to detect. But if we were just to try to feed that directly to a microcontroller or something to pick up, maybe it wouldn't be able to. So when we have our setup such that 1 and 2 are the same, 3 and 4 are the same, and let's give this so it's maybe our 3 and 4 we put at 10K, well 1 and 2 are at 1K. We can now, by that very small difference of 0.02, and it's now going to be something more readable. So it's very helpful when we have two signals that are going to be very close together, separated just by millivolts, but we can then amplify it to be in the more readable ranges of, being only 0.2 instead of 0.02 all the way up to, a couple actual volts. so it's more readable in that sense, and is able to then be a little bit more easy to use. Questions on this? No questions at all? Okay, well, that is it for OpAmps. So I will now require 3 questions out of you guys, and then we will go shift onto the powerless meeting. So 3 questions, someone go, before I start picking on people.
Do you know like the application from OpAmps for like for audio? Like I was like reading about it, but I'm not sure if you have any input from that.
Yeah, OpAmps are massively used in audio processing, and for a lot of the reasons of you're able to pick up very fine differences and small generated signals and largely amplify them so that they're actually audible and can distinguish between others. I can't say much on it because I don't do audio bullshit, but yeah, it's massive in audio.
Yeah, like I mean, like it is cool. Like I mean, I try to see some audio circuit, but it's like a bunch of OpAmp and analog circuit. So,
Yeah.
shit.
It's a very analog system. Someone else? When would we use a differential? Couple different places. Signal comparison is the big one. I believe. Geez. Braden is actually using it in the high voltage board for the high voltage measurement system circuits. So that is, we are taking our 168 volts and we are stepping it down to 5 volts so that we actually have circuitry that can read it. But when you drop from 168, 144 volt range to only a 0 to 5 volt range, your resolution is going to be very fine. So if you want to be able to still translate a 1 volt change on the high voltage side, which will only be millivolts on the low volt side, you would use something of this so that you can amplify that signal back up into a readable, a distinguishable voltage range.
Yeah, that's also how you do current measurement with shunt resistors? Need to have some sort of common mode rejection.
Yeah, that's the other thing. Current reading is typically done just through a shunt resistor. Current measurement, that is, which is you just pass your voltage through a very low resistance resistor, and you'll get very small voltage drops, which will relate to the current passing through. And with that, you can kind of figure out, again, you can amplify it, bring it back up into a readable range, and then you'd be able to tell what your current is. Kind of like an analog version of a comparator. Yeah, that's a way to see it. One final one. Elena, any questions at all through any of this?
Yeah. So I was basically what an op amp does is just steps up or steps down voltage. Is that? Did I get that right?
Yeah, basically, it amplifies.
Yeah.
But yeah, so it's in a sense able to both increase and decrease whatever your input voltage is.
Okay. So, like, what would be the like, when would you use an op amp instead of like a MOSFET or a boost converter? Because isn't that what like boost and MOSFETs do?
Yeah. So this isn't like, you wouldn't want to feed this 2 volts and then have stuff running at 5 volts. Like, you wouldn't want your output to be something 5 volts and you use that to power your circuit. Because most op amps, they can typically only source hundreds of milliamps. They're not good for sourcing the couple of amps that you would normally. And a proper boost or buck converter is much more efficient. This is more for instantaneous, like, signal level amplification, better for reading signals, and yeah, basically taking small signals and making them usable or readable, instead of using it as a power system.
Okay, gotcha. Thanks.
Yep. Okay. If nobody has anything else,